we are going to talk about the last concept of Chapter 1, which is acids and bases. Now, there's a couple types of acids and bases, and we'll go from most small or most restrictive to the largest classification of acids and bases. The oldest and the most specific classification is called the Arrhenius acids and bases, where it says that acids produce H plus and bases produce OH minus. So that limits us in our definition. It limits the acids to anything with a labile proton, and it limits the bases to anything with a labile hydroxyl group. So this is something like HCl, HF, CH3, COOH, anything with a labile proton that can be donated into solution. The OH donation, which from a base is something like NaOH, KOH, cesium hydroxide, any of these that have an OH. So this limits us really to mineral salts. The next largest group is going to be the Bronsted-Lowry definition of acids and bases. This is a little bit more general than acids producing H plus and bases producing OH minus. This says that acids are proton, which is H plus, donors, and bases are proton acceptors. So this indeed includes things like HCl, HF, CH3, COOH. So again, it's something with a labile proton that since it has a donated proton. However, this expands our definition of bases to things like, yes, we have NaOH and KOH, but this also expands our definition to include things like NH3, BH3 that can accept protons. If we're to draw the reaction between a Bronsted-Lowry acid and base, we can say that the Bronsted-Lowry base, we can call it B plus or B with a lone pair, and we can have our acid as HA, so this would be our base, this would be our acid. If we're drawing the arrow pushing, we're going to take the arrow, and it's going to grab that H since it's a proton acceptor, and the acid is a proton donor. It's going to push those in the bond back onto the A. What we'll be left with is a BH bond that's formed where B now has a positive formal charge, and A minus where A now has a formal negative charge. Remember that if B is the base, we're going to call this the conjugate acid, and if HA is the acid, then A minus is going to be the conjugate base of HA. So examples like this could include things like, so an acid could be, say, the reaction between H2O plus H plus gives us H3O plus. So in this case, H2O is acting as an acid, H2O is acting as an acid, or we can have something like H2O is acting as a base in this case. We can have H2O plus NH3, where we have then OH minus generated plus NH4. So in this case, H2O is acting as a base. In this case, H2O is acting as an acid. If we have a case where something can act both as a base and an acid, we call this amphoteric. So it's something that can act both as a base and an acid. Common amphoteric species are water, or hydrogen sulfate, or hydrogen phosphate, as well as dihydrogen phosphate. Things that can go either way. They can either accept a proton or donate a proton. So these are some common amphoteric species. The final definition of an acid and base is going to be the Lewis acid and base. So this is the most broad definition of acid and base. It includes a lot more than just things that look like acids and bases. And this says that an acid is going to be an electron pair acceptor. And this is going to say that a base is going to be an electron pair donor. So what does that look like? If, for instance, we drew the reaction between BH3 and NH3, and I'm not drawing these with geometry, but you would understand that this is a trigonal pyramidal species and this is a trigonal planar species. BH3 has a lone, has an empty p orbital since it's sp2 hybridized. What this means is we can show arrow pushing from the electron pair on NH3 into the empty p orbital on BH3, and this would form a what's called a Lewis acid base addict. So we'd have BNH3, we have H3B on the other side, and this would generate a minus and a plus charge. Got a minus charge. So this would be a Lewis acid pair addict. This is less common. This particular example is less common to organic chemistry. One that we will see in organic chemistry, say, is the reaction between OH minus and CO2. Now, OH minus is electron rich, so it's going to have space to donate electrons. So we're going to take this electron pair and attack the carbon, and that's going to push this bond into a lone pair on the oxygen. What we'll be left with is the Lewis acid base addict. We have OHC, O, this is a C, and then O, the minus charge. So we formed the carbonate ion, or hydrogen carbonate ion rather. In this case, we would call the OH minus the base, or the Lewis base. We would call the CO2 the Lewis acid. Another name that we see in organic chemistry is Lewis bases we call nucleophiles. They're going to be attracted to nuclei because they have extra electrons. The acid we call an electrophile. It's attracted to electrons. It's going to pull those electrons to it. So Lewis bases are always nucleophiles. Lewis acids are always electrophiles. The last portion of this section in the book is to how to predict equilibrium. So in order to predict equilibrium, we have to be able to predict acid strength or relative acid strength. In general, remember that the lower pKa is going to be a stronger acid. So the lower the pKa, the stronger the acid. There's two trends that we can look at in terms of acid strength. If we look at the halogens, the halogen acid, so we have HF, HCl, HBr, and HI. We see that HF is less strong than HCl, which is less strong than HBr, which is less strong than HI. This is because the bond strength is going to increase as we get to HF from HI. So bond strength increases as we go up a group. So what this means is stronger acids have weaker bonds. That is between the labile proton and the atom it's attached to. The other trend we can talk about is in electronegativity. If we look between C, N, H, O, and F, we see that CH4 is weaker than NH3. In terms of acidity, it's a weaker acid. NH3 is a weaker acid than H2O, and H2O is a weaker acid than HF. What this means, if we look this way, electronegativity of the carbon, the nitrogen, the oxygen, or the fluorine, electronegativity is going to trend as it does on electronegativity, is going to trend as it does on the periodic table. And we see that the the more electronegative atoms is going to generate a stronger acid, and that has to do about the pull of the bond. The other factor that we see in determining the strength of an acid is if we can stabilize, so this is a star, if you can stabilize the conjugate base, you're going to increase the strength of the acid. So what that means, let's look at HNO3, so nitric acid, so HNO3. So I'll draw on the electrons here. So if we remove this proton, we pluck off this proton, so we're left with H plus and NO3. Oops, it should be an N. NO3. You'll notice that this NO3, this resulting anion, this has an overall minus charge. This is going to have 3 resonance structures. So because the conjugate base, and remember we can label this would be our acid, this would be our conjugate acid, and this would be our conjugate base. Since we have 3 possible resonance structures for the conjugate base, we are going to greatly increase the strength of this corresponding acid. And that can be demonstrated with another example that I'll show here. So let's, for instance, compare the strength of these 2 molecules. So we have methanol, and we have formic acid. So we'll just add a generic base, so hydroxide, and we'll be left with H3CO- and HCOO-. So which one of these would you predict to be the stronger acid, methanol or formic acid? In this case, we see that methanol, when we lose this proton, we're left with an O- that's a point charge. This minus charge cannot be distributed anywhere else in the molecule. However, this O-, when we've plucked off a proton from formic acid, we can draw a resonance structure where we've distributed the negative charge over 2 oxygen molecules. So since we have this type of resonance in the resulting conjugate base, we'll see that this formic acid is a much stronger acid than methanol. And in fact, the pKa of methanol is about 15, and the pKa of formic acid is about 5. So it's a much, much stronger acid. So using these rules, we can predict equilibrium using the relative strength of acids. So for instance, say we had H2O plus HBr goes to H3O plus Br minus. So I'm asked the question asks which direction does the equilibrium favor, the left or the right, the reactants or the products. So we first identified what we know is equilibrium tracks with acids, with the stronger acid. So what that means is the stronger acid is going to push equilibrium. The stronger acid will always be in the reactant side. So we first have to identify our acids. In this case, we have our HBr, which is our acid, and our conjugate acid, which is H3O plus. Now, there's a couple good benchmarks for pKa's to remember. In this case, I know that the pKa of HBr is about -6, and the pKa of H3O plus is about -2. So in this case, the equilibrium would favor the products. I would say there's a couple good pKa's to remember. Going from lowest to highest, I would say the mineral acid, so HCl, HI, HBr, etc. These all are around 0, so these are pKa's. HCl, HI, HBr are all around 0. If you see this motif, these are our carboxylic acids. These are all going to be around 5. So that's something like formic acid or acetic acid. Those are all going to be around 5. Something like water or alcohols are going to be around 15. And then we get into things that really aren't that acidic. So NH3 is around 30. A C triple bond CH, this H is going to be around 30 as well. C double bond CH is going to be around 40, and C single bond CH is actually going to be around 60. So these are good benchmarks to know just when we're looking at the pKa's in order to predict equilibrium in a particular acid-base reaction.